Okay, so we get that information back to the retina, to the rods and cones. So the photoreceptors, they are our sensory receptors that are doing the transduction. Transduction, remember to sing it, it's a very exciting thing. We're going to go through the differences in those rods and cones, and then what that means as far as our particular, how we see as humans. So the differences, they differ in their physical appearance, they differ in their distribution across the retina, they differ in their wiring, which we're going to walk that through that and discuss how the wiring means that the cones are going to give us more acuity and the rods are going to give us more sensitivity, and by that I mean sensitivity to dim light, to low light levels. We'll talk about some clinical issues at the level of the retina now, and then that will start to show you the functional significance of the rods and the cones, but we'll go through the functional significance as well. So they look different. Their appearance is different. The rods look like rods. The cones are smaller, and if you use your imagination, they look like cones. This is a scanning micro pictograph of rods and cones. Their distribution across the eye is different. So if we're looking at 0 degrees, and the way they do this visual angle is if I'm looking at 0 degrees, that is where I am foveating. That's where my eyes are pointed, regardless of which way they're pointed. The 0 degrees is my foveal vision. And around that, because the retina is round, we're going to have these degrees like the degrees of a circle. Okay, and so if you look at the 0 degree mark, the red line is the cones, and you'll see we have lots and lots of cones packed into that foveal vision, and then they trail off really quickly, and we have some cones out in the periphery, about the same amount of cones as other areas of the periphery, and they're just not very many cones. If we look at the rods, the blue lines, you can see that there are no rods, none in the foveal vision. Okay, we're going to end up coming back to that. As we move out into the periphery, as we get close to the fovea, we'll see this a large number of rods. We want pretty good vision right where we're kind of pointing our eye, close to where we're pointing our eyes, even if we're in the dark, but then those two are going to trail off. As we get farther and farther into the periphery, if you kind of bring your consciousness to your periphery, like I have my hands out here, it's kind of blurry, right? The other thing this picture shows is that blind spot. So that brown area is where the optic nerve is going in, and you can see it better on that picture on your left as well than you could before. The optic nerve, the optic nerve is leaving. It's not going in. The optic nerve is leaving. We're going to take the axons from the ganglion cells that are going to bring that information to the brain. They have to leave the eye, and then we also have blood vessels going into the eye. And so there are no rods and cones there. And I typically hand out a really quick and dirty, cheap example of us actually seeing our blind spot. But if you want to see your blind spot or become aware of your blind spot, you can print this page up whole, close your left eye, and then line up the cross so that you're looking at it with your right eye, and move the paper towards you until the mouse disappears. And what do you think happens to the stripes? And after we've done this in class, people are they're pretty good at guessing usually. I do this with a blank piece of paper and just an X, Y, Z, and your brain fills in with the piece of paper. Your brain is going to fill in those stripes. You could also, if you want, if that one didn't work very well for you, because I have noticed that some people tend to move one of their eyes a bit more. You really need to keep your eye fixated on the fixation point. You can print up this page, I think as a whole, but I think half page might even be better. I haven't actually used this one. I've used it from the book, but then you close your right eye and you look at that fixation, move it back and forth. And what do you think happens in the middle? I'll let you think about that. Okay, so appearance, distribution, we're going to talk about the wiring. And this is showing a really simple example. Our photoreceptors are on your left. The back of the eye the pigment epithelium there is that little brown line, the photoreceptors, and then we see some neurons. And right now, I'm going to ignore the horizontal or the neurons that are going in the perpendicular kind of way and just kind of talk about bipolar cells and retinal ganglion cells here and there. And notice that the light is coming in from the right. So the light's coming through all of those optics of the eye, the mush, the vitreous humor, all of those neurons, and going to the very back and hitting those photoreceptors at the outer discs at the very, very back. We have about 126 million photoreceptors per eye. Those photoreceptors, when they absorb a photon of light, are doing the transduction. Transduction! So here we have this electromagnetic energy that's out in the world, and I'm changing it so that the brain can understand, right? I'm responding to it, changing it into action potentials. They are going to communicate out to the bipolar cells, and we're going to see some convergence. The bipolar cells are going to communicate out to the retinal ganglion cells, and we're going to see some convergence. And so we've moved in this picture from 4 to 3 to 2, but in the real world, we're going to move from 120 million rods and 6 million cones out to 1 million retinal ganglion cells. So there's a lot of convergence of information. Here I've made this a little bit larger and corrected the mistakes that came from the publisher's files. These mistakes were not in the textbook, but we right now are ignoring those horizontal and amacrine cells, and we'll come back to those when we talk about inhibition later. Okay, so the wiring between the rods and the cones is different from each other. The cones have a more linear circuit, and in the fovea, they have a linear circuit, one cone communicating to one retinal ganglion cell. So that's that 1-to-1, and that's going to give us high acuity or high ability to see really small, detailed things, high resolution. It's all ways of saying the same thing. Again, that's why I point my eyes to look at tiny letters. If we get out into the periphery, we have this convergence. And for the rods, that convergence is about 120-to-1. There are about 120 million rods per eye and about 1 million retinal ganglion cells. So the convergence is about 120-to-1. For the cones, there are 6 million cones per eye and about 1 million retinal ganglion cells. So that convergence out in the periphery is more like 6-to-1. And so it's actually a spatial summation. So if you think about how this is happening on the back of the retina is across space, and we're going to have a bunch of rods in a particular space, right? 120 of them are going to communicate to a single retinal ganglion cell. And that spatial summation is going to give me increased sensitivity for dim, low light levels, but decreased resolution, decreased ability to see like those really small details. And I'm going to go through this with an example. So let's start with the picture on your left. On the very left, we're going to look at, I'm going to call that a bipolar cell. And you can see that there are 5 rods communicating with that bipolar cell. In the next picture over, in that same image, there are 5 cones communicating to 5 bipolar cells. Okay. And they each have the linear circuit. We're looking at a linear circuit there. So let's pretend we're in a low light level where we're going to call it, and these are arbitrary units, we're going to call it 2 units of light or the light is causing 2 units of activation. We can call it 2 units of light. 2 units of activation is better. And we're going to say that bipolar cell, its threshold for activation, remember we talked about thresholds, like my neuron has to reach a certain threshold and then it'll fire. Let's say its threshold is 10. Okay, and so we're in this dim light, and that light is hitting these 5 rods, and so those rods are each giving 2 units of activation. So it's 2, 4, 6, 8, 10. 10 units of activation, and that bipolar cell fires. So I actually see the light out there. If we look at what's happening with the cones, I'm in this dim light. Each of those cones is getting hit by a light and communicating 2 units of activation to these bipolar cells that have a threshold of 10. So first cone, I just don't see it. Second cone, I just don't see it. Third cone, I just don't see it. Fourth cone, I just don't see it. Fifth cone, I just don't see it. With my cones, I just don't see that dim light. Okay, let's turn the light levels up to 10. I'm in brighter light now. If we look at, and we'll just pretend that we're not utilizing this and then needing it to regenerate. We're just going to say now, each of those, the light's 10 units, I'm firing. My rod is firing at 10 units. I've turned up all of those 5 lights to 10. And so now I get, with the 5 rods hitting the 1 bipolar cell, 10, 20, 30, 40, 50 units of activation. My threshold is 10. What happens? Yeah, I'm letting you think about that. I fire faster, right? That's how a neuron communicates signal strength. I'm in a brighter light. I'm getting more activation. I'm just going to fire faster. If we look at what's happening with the cones, I get 10 units of light. I see it and I get represented in the brain. The second cone, I send 10 units. That bipolar cell, it fires. I see it and it's that is represented in the brain. The third one, I see it and it's represented in the brain. The fourth one, 10 units, I see it and it's represented in the brain. And the fifth one, 10 units, I see it and it's represented in the brain. And so now we can see how also the cones are going to give us acuity. And I'm going to move over now to the image on the right, where we're seeing those same rods communicating to the single bipolar cell up at the top, and the cones each having their linear circuit in the bottom of that figure on the right. And so if we look at what's happening with the rods, and I have 2 lights and they're up there at 10 units, right? I'm going to get my bipolar cell. It's going to get 10, 20 units of activation. It's going to be firing pretty quickly, but not as fast as when it was getting 50 units of activation. But it doesn't know where that light is, right? I can move those lights and I can hit the 3rd and the 5th. I can hit the 2nd and the 5th or the 1st and the 5th. Those rods aren't telling me where exactly that stimulation is coming from. So I've given myself increased sensitivity to dim light, but I've lost that resolution, that acuity. If we see what's happening with the cones, I'm out in bright light, 10 units of activation. In the first example, when I'm hitting the 4th and 5th cone, it looks like there are 2 lights right next to each other. And if instead I move one of those lights, so I'm hitting the 3rd and 5th cone, I have representation of the brain of each of those cones. And so first one is telling me there's no light there. The second one's telling me there's no light there. The third one is telling me there's light there. The fourth one here next to it is telling me there's no light. And the one next to that, the 5th one, is telling me there's light. So I can see that there are 2 lights and they're separated from each other by a little space in between. So I get that resolution or acuity. Turn those lights back down to 2 and I don't see anything. Turn those lights down to 2 up at the rods. I still see something's out there. I can't tell exactly where, but something's out there. Okay. The wiring's a pretty complicated topic, so I like to take this little break and just review a little bit and look forward a little bit. Remember, when we're comparing the cones to the rods, the cones are about 6 billion per eye. They're mostly in the center in the foveal vision. They are not sensitive to dim light. They are sensitive to detail. They give us the acuity. The rods, they're about 120 million per eye. They are in the periphery only. They are not in the central vision at all. They are sensitive to dim light, but they are not able to see those details. And now, part of the looking forward as well, we're going to see some of the functional significance that the cones are going to be what give us color vision. The rods stick with black and white vision.